Hi guys, in this video I need to demonstrate how to derive the ordinary least squares regression parameters. My name is Brian. I'm studying at the University of Solon and these are my details. So I intend to demonstrate how we derive the OLS regression parameters in a bi-variate framework. So a bi-variate framework is a scenario in which you have two variables, one the dependent and one independent variable. B, what you see is the slope. A is our intercept. This is the error term which captures the impact of all other factors that may affect Y but are not necessarily included in the analysis in the model. So let's think of this. Okay, let's assume that this is a demand function. Okay, so that this obviously would be a minus if it is a demand function. So we assume that this is our price and this is the quantity demanded. So now mu here, you can think of it as a factor which captures the influence of other variables such as income of the consumers, advertising, price of other goods and so forth. And that's the role of mu. Now I want to show you how we derive beta and beta A using the ordinary least squares regression technique, because the OLS is a model, is a method, sorry, not a model. This is the model. The OLS is a technique which allows us to get the unknown values of beta and A, which is our intercept. Now, the way we write our model is this. So we start with a specification which looks like this. So this is normally referred to as the population regression function. Okay, so this is the intercept, this is the slope, and this is our explanatory variable, this is our dependent variable, and this is our error term. So the intercept is just the value of y here when x is 0. This will be x. Okay, so that the gradient here, which is this one, given by the change in y over the change in x, this would give you your beta 1, this one, right? Now, so what happens is when we have observations, I am gonna make an assumption that I have a sample size with only 3 observations. Okay, so I'm making an assumption here that the regression that I want to estimate is 3 observations. Okay, so I'm assuming that it has 3 observations. So I'll write here observations 1, 2, 3. I'm randomly assigning these numbers. Okay. Now, so what we do is with this data set, the ordinary least squares helps us get the values of these unknown parameters. So in other words, the OLS will get the estimates of beta naught and beta 1. So we have beta at naught and beta at 1, right? When we get these values, let's assume we get them as 2 and 0.5. Okay, so let's assume that beta at naught after estimation is 2, this after estimation is 0.5. So what it means is For us to get the predicted value, this would be the predicted value. We get it by adding our intercept to the product of our slope times we substitute the values of x. So we're going to take 3 and substitute it here. You see, to get the predicted value. So this is the estimated value. Okay, the one that is predicted by our model. So to do that, let's come here and introduce y-hat. Okay, it's not a nice y-hat. Yeah, much better. So what we need to do here is to substitute all the values of x, but in 10. So we start with 3. So we have 3 multiplied by 0.5. This is 1.5, right? So 1.5 plus 2. So we have 1.5 plus 2. So we're gonna write 3.5 here. Okay. Next is 1 times 0.5, which is 0.5 plus 2. Okay, which means we have 2.5 here. Sorry, 2.5 here. Okay, next we have 4 by 0.5, we get 2 plus 2, which is 4. So these are our predicted values. So these are our predicted values. These are our predicted values. Now, because you see that to get this one, we needed this and this and this. We needed 3 things: the values of x, the estimate of beta 1, and the estimate of beta naught, right? Which means that we can look at this expression, this part, as our y-hat. This is what we only needed to get this, right? So we can rewrite this equation as y is given by y-hat plus u. Okay, which means if we want to get u, if we make it subject of the formula, it's just u is equals to y minus y-hat, like that, right? So if you come here to get u, which is the residual, it's now easy. It's now this subtract this. Okay, so 2 subtract 3.5, we get negative 1.5. Okay, and then 4, we come to this 4 here, subtract 2.5, we get 1.5, and then 2 subtract 4, we have minus 2. So that's how we get, these are our residuals. Now that we know these basic things, we now need to solve this one and this one, the formulas which enable us to get 2 and 0.5. Remember, 2 are just random numbers that we just picked from our head for illustration purposes. Now to solve for beta naught, it's important for you to know that the ordinary least squares minimizes the residual sum of squares. The ordinary least squares, it minimizes the residual sum of squares, right? You should know that from the beginning. Now the starting point is this one. Let's expand this one. So we can expand this one by saying y is equals to y minus open bracket. I'm gonna replace this with this because it's basically the same thing. I'm gonna say beta at naught plus beta at 1x, and then I'm gonna close bracket, right? This is the same thing. Now, to get rid of the brackets, to remove the brackets, we multiply everything inside the brackets by minus 1. So we have u is equals to y minus beta naught minus times plus, it's minus. There we are. So because we said the OLS minimizes residual sum of squares, right? We have to introduce the summation side and the squared. So we have summation of the squared is equals to the sum is minus close bracket squared. Let's call this equation 1. Right. So what we're gonna do here is let me just say let this be residual sum of squares. What we're going to do is to differentiate this equation with respect to our regression parameters. So we need some calculus. So we're going to differentiate this specification with respect to beta naught first, and then we'll go to beta at 1. Now to do that, we apply what is known as the chain rule. So the chain rule says that if we have a function which looks like this, if we have a function like y is equals to 2 open bracket 3x plus 1 raised to the power 3. The chain rule says that we first define u by this expression inside here. So this means actually that we have a new specification which is u equals to 3x plus 1. Right. So if we define u this way, so technically it means that we can write the y function as y is equals to 2u raised to the power 3. Now the chain rule would then say that the overall derivative with respect to x is a product of two terms. The first is the first derivative of the y function with respect to u, and the second is the first derivative of the u function with respect to the x. So it will be dy du multiplied by du dx. So let's start with this one, dy du. We go to the u function. So using the power rule, dy du is 3 by 2 then 3 minus 1, which is equals to 6u squared. Okay, now let's go to this other, let's solve for this other one. So du dx is equals to, where do we go? We go to the u function here. So this is equals to 1 times 3, okay, and then x raised to the power 1 minus 1, which is equals to 3. So now, because it's a product according to this formula, so it's 3 times this, which means we can write this as 18 u squared. Okay, so it's simply 3 times 6 and then u squared. Now, because we know this u from here, the final answer we can write it as 18 open bracket 3x plus 1 raised to the power 2 from here. Okay, so this would be the final answer. Now let's apply the same reasoning here. Okay, so you're gonna imagine in your head that this inside is what we call YU. Okay, so you can imagine this as RSS is given by sum of u to where u is equals to y minus beta h naught minus beta h1 x, so that the overall derivative with respect to beta naught will be given by first the residual sum of squares du times du to beta h naught. Okay, so from here, which is this specification, this is gonna be, so let's start with which one do we start? Let's start with this one. Okay, let's write it here. So this is gonna be du is equal to, we go to this u function, right? No, we go to this one. So if we differentiate this one, this is gonna come down here. So we have 2 summation of, we put u and then 2 minus 1, which is equals to 2 summation of u. This is the first part, right? Okay, so you can think of this one as this first part. Now let's go to the second part, which is this one. Now that part is du d beta h naught. Now this is equals to, we go to the u function, we differentiate with respect to beta naught, right? So this is gonna be minus 1, right? Because it's 1 times minus 1, and then you have beta h naught raised to the power 1 minus 1. So the answer is minus 1. So it means then we have the first part. So we have the first one was 2. So this here is what we got from here, and this is what we got for this part, which means we have minus 2 summation of u, right? And what is u? U is this one. This is u. which means that we can rewrite this one here. So the first overall derivative here would be minus 2 summation of u here, like this. And then since we know our u, this would be minus 2 summation of open bracket. We insert this because this is stable. So it's y minus close bracket, like this. We equate this to 0 because at the minimum point of a curve, the slope is 0. Remember, we're minimizing the residual sum of squares. Okay, let me try to get space from the top. Now, so from what we have so far now, we need to make beta height not subject of the formula. Okay. So from this equation here, I'm taking it here, right up here. Okay. So I'm gonna rewrite it as this. Have I left anything? No, it's fine. It's equals to 0. So I'm gonna divide everything by minus 2 to get rid of this negative 2. Okay. So we have this. It will be like this. So the minus 2 goes away. So we have this expression. Now let's multiply everything by summation sign. So we have summation of y minus summation of beta, negative beta naught is negative n beta naught, beta 8 naught, minus x is equals to 0. Now, why is it we're saying n beta naught? Now, just to think of, okay, let me just give you a very quick example. So, if we have observations like this, 1 up to 3, our n here is 3. Our n is 3. Now, if we didn't have x here, and we had beta 8 naught, we had beta 8 naught. Now, beta 8 naught would be a constant, right? It has a constant value. So it means if it is 3, then it's 3 throughout. Right? It's 3 throughout. So the summation of this beta naught would be 3 plus 3 plus 3. If we know our n, if our n is 3, then we say 3 plus 3 plus 3, which is 9. 3, 6, 9. Right? So it would be 9. This is the same as if we know, this is to say 3 is our n, 3 times 3, it gives us again 9, right? That's the reason why we say summation of beta naught is n beta, because our n here is 3, and we have a constant value of 3, 3, 3, so it's just 3 times the number of observations that we have. Then we get summation of betas. So in other words, this is beta naught, this is beta naught, this is beta naught. So the summation will be beta times n, okay, which is 3 times 3, which is 9. That's why we write it as n beta naught. Okay. Now this is x. It's now appearing like a plus. Now let's make n beta naught subject of the formula here. To do that, we add n beta naught both sides. So here we add and then so that we have n beta f naught here this side. Okay, so I'm gonna so you can see that this and this go away. So I'm gonna rewrite this specification starting with n beta naught. So we have n beta h naught is equals to this minus this. So we have summation of y minus beta h1 summation of x. Okay. So now from here we can divide everything by n. So this divided by this. So we have our formula is beta h naught is equals to this summation of y divided by n. If you divide the total number of observations divided by the sample size, if you say 2 plus 4 plus 2 divide by 3, you get an average. So this will give us the average value of y. So it's y bar minus beta h1, which from here beta h1 summation of x divided by n, it gives us x bar, the average of x. So this will be our final formula for the intercept. This one. That's our intercept. Now let me try to get a little bit of space here or to avoid confusion. I will derive for beta 1 in the next video. Now what we actually need to do is to simply differentiate this residual small squares function with respect to beta 1 and make it subject of the formula. Thank you very much for listening.